It's fun.
Hey, y'all. I'd like to congratulate the 7 of you for making it out this morning after last night's after party. But I do feel like we need to talk. A little awkward, sorry. But I do feel like we need to talk about this like metaphor that we have going on for big data pipelines as watershed. 1 second. Excuse me. Flowing in streams, collecting in lakes, and God, especially lakes. I don't think, like, do y'all understand? Nothing good winds up in a lake. Maybe you don't live by a lake. Mostly it's just like Christmas trees and like incriminating evidence, anything the dump charges you extra for, that winds up in a lake. People you don't like. Not answers, right? Like, not answers. And that's particularly true from, I feel like, a user experience perspective. Like, generally speaking, the lake is not anyone's destination of choice when they strike out in search of enlightenment. It's just conceptually a bonkers analogy, is all I'm saying. With the possible exception of like forensic technicians, nobody heads to the lake for answers. And I'm dwelling on the lake thing a little bit because it's easy, but I think more generally, this entire watershed metaphor is actually kind of unhealthy because I believe it encourages us to think about big data and streaming pipelines in kind of nihilistic and reactive ways. And I'll take a minute to explain what I mean by that by further belaboring the metaphor. So this is the creek that runs by my house in southwest Montana. It doesn't have a name. And it's about a half-mile downstream from where I took this picture last spring, that my creek joins Mission Creek and then flows another 5 miles into the Yellowstone River. Now, Yellowstone River is big. By the time that my creek joins it, it's been gobbling up watershed for 50 miles. So it's already like this substantial flow of water. And it'll keep flowing for another 100 more miles before gobbling up the Bighorn and the Powder River and countless little creeks like mine, before it joins the Missouri River, which continues to gobble up watershed all the way across the Dakotas, before finally joining the mighty Mississippi River just north of St. Louis. The Mississippi River is the 3rd largest river in the world, drains about 40% of all the watershed in North America. It is, by the time the Mississippi empties into the Gulf of Mexico, 2 miles wide, 200 feet deep, visible from space, big, right? This is an unfathomable body of water. And I know you're hungover, so I'll give you a moment. Go ahead, try to fathom it. You can't, right? It's unfathomable. And that's how watershed works. That's the story of watershed. Watershed is the story of slow accumulation and burgeoning incomprehensibility, where pretty little creeks that aren't anyone's problem Katamari snowballs into problems that are, beyond what anyone can deal with. It doesn't help to think about data this way. Because what can you do with this but like shore up the banks and get out of the way? Pray for a dry summer. Like, you can't get ahead of watershed. It's watershed. It's got to flow somewhere. And I grant a lot of data gets treated this way, as if there's like nothing to be done but dig a lake. But I think it's more helpful to consider instead that your telemetry data is born torrential. It's torrential at birth. And what I mean by that is incomprehensible magnitude is your data's native state at the moment of creation, right? Doesn't matter that the whole represents an accumulation of disparate collectors, nor does it matter that it has not yet traversed from here to there. The distribution of your data in corporeal space is irrelevant to the scale of the problem. And crucially, unlike watershed, which cannot be reduced but only directed, data can be reduced, right? It can be filtered, combined, made smaller in ways that do not affect the underlying truth that it represents. And therefore, really, it's the opposite of watershed in that rather than a story of slow accumulation and burgeoning incomprehensibility, telemetry data is sort of an entropic explosion, right, that we must reduce into some kind of truth. Filter, aggregate, deduplicate, reduce. Our job is to give scope to that which was born incomprehensible. And this talk is about why I think we should take action to that effect as quickly as possible and how we might go about doing so. My name is Dave Josephsen. I engineer on the network control and optimization squad at Fastly. My day-to-day work consists of building and maintaining telemetry pipelines that feed autonomous systems that direct traffic on Fastly's global software-defined network. One of the systems I feed is a system called Autopilot. The problem it solves fundamentally is to make a three-dimensional decision about network topology. What is the fastest, least congested, most inexpensive route back to a given client? And having solved that problem, Autopilot sort of expresses its opinion as a BGP route override, which is respected individually by Fastly cache nodes running in Fastly's global fleet. Excuse me. In order to formulate that opinion, Autopilot must know the current link capacity, utilization, and outbound peers, link performance, utilization, and outbound peers for every switch port on every switch and every Fastly point of presence worldwide. And it needs to know all that kind of constantly within sort of a constrained window of time. And that telemetry comes from various sources, application layer logs, eBPF filters, SFlow from the switches, distributed active measurement systems. These are systems where Fastly is basically like pinging itself across the internet. The telemetry from these pipelines is also repurposed and used widely by human operators who are trying to understand network behavior at a tactical level, as well as more strategic planners within Fastly who are trying to understand global trends and lofty patterns and how Fastly should grow to provide the best service to its customers. The low-resolution shape of all NCO telemetry pipelines is a bunch of little collectors, all writing samples to some common persistence layer. And then generally speaking, we point the users and Grafana's and daemons at the persistence layer to sort of get the answers that they're looking for. And the first thing I want to observe with you this morning is that regardless of its components, the further down any pipeline each sample traverses, the more expensive the pipeline becomes to run. Naively, if you have 500,000 samples, and you traverse every single last one of these samples past collection agent switches, ETL, pub sub, queries, queues, and into sort of a persistence layer, you need more transport, more hardware, more storage, more instances to sort of collect and process and store those 500,000 samples per second versus sort of half that many, right? The same is true of latency. If you freeze horizontal scaling at size X, 20 billion samples take longer to traverse pipeline X than 10 billion samples take to traverse it. So speaking widely, the cardinality of samples traversing your pipeline linearly impacts both your end-to-end latency and the cost of the pipeline in dollars and cents. And the second observation I want to make, this is also true the more data you have at rest. So naively, your queries take longer to run the more data you have to scan, right? It's not really fancy, big thought leadering ideas up here from Dave this morning, but all fancy columnar storage hacks and optimal key-based sorting being equal 20 billion rows in the same time span and sorting context of data, right? Takes more time to scan than 10 billion rows in the same time span and context, right? So we have these three dimensions. And each of these, I believe, are common to and dictated by the design of every data pipeline. And all three vary directly by ingestion volume, okay? More samples, more cost, more latency, longer query time, and transitively, fewer samples, you reduce all three. Simple, obvious. I don't think I'm being controversial in any of that. And by the way, I very intentionally sort of labeled these as budget dimensions on this slide because one of the points I'd like to get across to you this morning is that we should be treating these as currency and we should be spending them more wisely than I think a lot of us are today. Because circling back for a moment, I think what watershed thinking encourages us to do is to optimize for end-to-end latency when we build data pipelines rather than sort of budgeting based on the workload. So essentially, what we're being expected to do is spend tons of money on big fancy streaming infrastructure to carry 100% of everything into the persistence layer as quickly as possible. We sort of tell ourselves it'll be fine, we'll sort it out with a group by later. And essentially what I believe that means is that we take whatever latency we could be budgeting on data reduction toward the source of the data and we multiply it in pipeline traversal. And then we write it into stone in the persistence layer. So by not properly investing in data reduction early on, we wind up paying a much higher price for the same amount of truth, right? And not only is that price sort of woven into the fabric of the tail end of the pipeline, but also in the time that it takes to eventually query the data set. So my sales pitch to you this morning, take it or leave it, is that small investments in latency in the early stages of a pipeline can pay off logarithmically in dollars in query time later on. So how do we spend that capital? Let me introduce you to a couple friends of mine. They're old and dear friends to me at this point. This is Poe and the Pug. Poe is the point of enrichment. I expect you to laugh at that last slide, by the way. You're laughing in my head, it's fine. Poe is the point of enrichment, and Pug the point of aggregation. Sort of a belabored acronym, fine. Together, I believe that these guys define not only the technical constraints of a data pipeline, but also the cost of the pipeline in dollars and cents. So when you understand how Poe and the Pug interact in a data stream, you understand what trade-offs the designers made when they built the pipeline, along with sort of what their priorities and constraints were. The point of enrichment, is where raw samples take a form we might consider persistable. And I'll give you an example. Extremely boring one, if you'll bear with me. When we get an SFlow message from a switch at Fastly, it contains an index number that represents the physical port upon which the sample traffic entered, and another index number that represents the port upon which that same traffic exited. Problem is the index number is meaningless to humans, but we can use sort of a metadata service to derive all sorts of useful info from that index number. The port profile, for example, tells us whether this switch port faces inward toward our systems or outward toward the internet. So when we have a flow sample that entered a switch on an inward-facing interface and exited the switch on an outward-facing interface, we have what you might call outbound traffic. So my point here is that we can derive traffic direction from port profiles. We can derive port profiles from port index numbers. And that's sort of why we perform enrichment. But a lot of these samples maybe we don't care about. For example, at Fastly, we don't care about samples that entered and exited on inward-facing ports because that's just cache nodes talking to each other, what we call internal traffic at Fastly. But hopefully now you can see that in order to filter out internal traffic, we need port profiles. We don't have those until enrichment happens. And that's sort of the story of Poe. The point of enrichment is intertwined with our ability to filter the sample set. Right? We usually can't filter until we enrich. Sometimes we can, but usually not. So we want to enrich as early as possible, right? Like in the pipeline, if our goal is to filter as early as possible, because again, the further those samples traverse, the more expensive our pipeline becomes to run. And also the further those samples traverse, the more latent the pipeline becomes. But we can actually do better than just filtering, which brings me to my other friend, Pug. Don't tell Poe, he's the favorite of the two. He is a magnificent creature. The Pug can make data pipelines orders of magnitude less expensive to run. And I'll give you an example of how he works. Using the same sort of port index numbers example as before. Let's pretend that a flow sample only contains these four pieces of information: an epoch Unix timestamp, interface in and out, and the number of bytes sort of transferred in the sample. And now let's say you have two of them, and they're 1 second apart from each other. And their interface IDs are identical, entered same port, exited same port. Well, instead of putting both of these samples on the wire and sort of transferring the same data mostly twice, we can just take the max of the timestamps, the sum of the bytes, and send one sample instead of two. And poof, 50% data reduction, right? We've cut our row count in half. And that's generally how aggregation works. The absolute most expensive possible instantiation of the Pug, therefore, in any given data pipeline is the one that places the Pug in the persistence layer. And we talk about, when we take the watershed approach and we say, we'll just use group by, we'll throw it all in BigQuery, it'll be fine. This is essentially what we're doing. But if we're performing some upfront aggregation closer to the data source, like in this example, that places the Pug sort of in the cheaper seats, which takes potentially a load of computational load. I said load, sorry. Off of the pipeline. And this is another good argument, by the way, for situating Poe as close to the source as possible, because we often need to enrich before we can aggregate. But there's an obvious downside to the use of Pugs. They don't come for free. Looking back at our example, should be pretty obvious that in order to combine these two samples that are 1 second apart, you need to delay the first sample by a second. So Pugs have a linear latency window associated with them, right? The longer you hold the window open, the better the compression rate you'll achieve. But while you're at it, you'll also introduce latency into the pipeline equal to the size of your window. And that latency will stack, right, with any other latency that you have sort of downstream. Hence, latency is the budget item. You need to spend it and spend it wisely. You don't need to. I do. You can if you want. We should spend it wisely. My personal experience, for what it's worth, to misquote Paris Hilton, Pugs totally worth it, right, if you spend wisely. So let's talk for a second about how to spend your budget. Because it turns out sometimes you can get Pugs for free, and these strategies generally kind of center around the kind of workload you're dealing with, what tools you have at your disposal, maybe your customer use cases. Now, one of the measurement systems that I inherited about a year after I joined Fastly was a system that sampled HTTP connections. And the pattern was it would take TCP connection stats from eBPF, it would combine these with request logs. So the system worked kind of like a transaction fulfillment thing, where it would keep a bucket open, like representing the connection in memory for the lifetime of the connection. And then over time, individual request samples, which represented sort of like requests traversing that connection, would pile up inside it. And each of these was represented by a row in the database. And historically, this had been one of those systems where the Pug was kind of in the VIP section, living it up in BigQuery. And it occurred to me that we could insert an additional Pug into the runtime. Like, we can, within the context of a single connection, aggregate all of these request samples down to maybe a handful of rows without adding any latency to the system, because you know, the latency was built into the system. This was held in memory for the lifetime of the connection anyway. And this is a huge success for cache node resource utilization. It cut an order of magnitude off this system's runtime memory, and which, you know, of course, translates to an order of magnitude fewer samples on the wire and in the persistence layer. So for essentially a 0-second investment in pipeline latency, we got a cheaper pipeline that queried more quickly, and also took some resource burden off of the cache nodes. So sometimes you'll have a system like this, where the latency is kind of already built into the mode of collection, right? But these aren't always obvious. And one example of where it's not always obvious is HTTP API boundaries, where it's pretty common practice to sort of buffer your payload, right? To decouple the input set from the number of HTTP requests you make upstream to sort of offload the data. Anytime you're buffering samples, you can usually hide a Pug in the buffer and get some row reduction in the bargain. Another way to hide a Pug, is if your downstream systems operate on windowed telemetry, and you'll see this pretty often with autonomous controllers where they need to compute a result, right? And they don't want to appear to be flapping, like going back and forth, right? So they'll generally operate on like a block of statistically significant data, and they want it to be fresh data so that they themselves appear to be, to react quickly. But usually not too fresh to the point where they might make a consequential decision based on incomplete or like otherwise not smooth data. So they'll choose, say, like the previous 2 minutes of data to operate on, right? And that's usually a pretty safe bet. If you can read papers about systems like this, like there's Meta, the augmented traffic control stuff, or Google topology control systems. You'll see that they always have these sort of like windows of latencies built into the system's control loop. And this provides us this little Pug zone of time where we can kind of insert like a 15 or 20 second Pug into the pipeline wherever we want before query time. And we can perform all kinds of row reduction without being noticed, right, like by the downstream system's control loop. I have a workload like this at Fastly today, and actually what you're looking at here is a graph of the reduction ratio on that workload. It's the number of inbound samples literally divided by the number that we actually wind up sending. So we quantify Pugs at Fastly. And in this system, depending on traffic volume, that ratio can raise above 50%. So for this workload, that's 500,000 rows per second. We no longer have to queue, persist, or scan at the cost of 15 seconds of delivery latency, which, you know, to misquote Carl Sagan, billions and billions, right, of rows swallowed transparently by a single well-placed Pug. If the downstream system that we're feeding is constrained to a time window, that equates to a budget increase for us, right? And we can get a lot done. We can get a lot done spending that budget wisely. So add to our list any systems where the stream is being consumed by time-oriented windowed processes. And that's a pretty strong list, I think, of ways to get free Pugs. But I have one more, and this is particularly powerful for those of you who might inherit sort of a large unwieldy pipeline, which I have several times now. And in that situation, it's often the case you'll find systems are directly talking to each other, either in like a sort of a microservices context or via HTTP. And having been in this situation a few times at Fastly, I found it's often useful to sort of resituate workloads like this around a queue. And I'm going to say specifically Kafka, just because I like it a lot. I've become very good at sort of wrapping Kafka producers and consumers with Pugs. The general idea is that when you have a system like this where the pieces are tightly coupled, sometimes it's a light lift, honestly, to just sort of resituate them around Kafka, because it's common practice for Kafka consumers to sort of batch read from a topic. So you can pretty naturally like wedge a Pug in there. You have so imagine you have a thread. It's basically just reading 1,000 messages off a queue. And since you're buffering in there anyway, you can just sort of implement a Pug into the thread, see if there's any opportunity for row reduction within that just sort of subset of 1,000 samples. I want to observe what's happened here in this slide, because I believe this is kind of an emergent property of wisely budgeted Pugs, which is also a property I feel like we're kind of encouraged to disregard, which is you can have more than one Pug. I mean, to misquote Billy Joel, Pugs, awesome, man. Why would you want just one? Why not Pugs everywhere, right? Like, why not pre-enrichment aggregation, post-enrichment aggregation, Pugs in the persistence layer, Pugs built into the HTTP middleware, right? Like Pugs wrapped around the producer consumers. Pugs everywhere you can shove a Pug, in my humble opinion. And when I say we're encouraged to kind of disregard this property, what I'm talking about is the watershed metaphor again, the cognitive pattern that a pipeline consists of source, transport, and persist. Aggregation is merely a feature, right? Supported by your transport framework and nothing else. It has one place. See, it's right there in the center of the architecture diagram where you'll find the trademarked logo for whatever your chosen whiz-bang center of the universe streaming thing of the month is. And I believe the reason these architecture diagrams take essentially the same shape is the underlying belief, again, that there's nothing for us to do but sort of direct the deluge, right? There is no viable strategy but to make a massive monetary investment in some grandiose stream processing framework and kind of hope for the best. And to my mind, this amounts really to just sort of like a one Pug to rule them all strategy. Like there will be one centralized point of aggregation in your pipeline, and therefore a single strategy for aggregation, which will eventually discourage you from using it in favor of just digging a lake. And that's cool. I mean, you can be successful doing that. You know, totally. You can just sort of say to yourself, I have no idea what's coming in. I'm going to fart it all into a lake and hope for the best. And maybe we'll use it, maybe we won't. But personally, I've had a way better experience sort of combining custom workers situated around queues with small, nimble, purpose-built Pugs. These Pugs, they disappear into the workload, they pull their weight, unlike these spoiled brat flaunting peacock Pugs, which are, like in my opinion, kind of here to be seen, expensive to maintain, and in my experience, they always sort of become burdensome and inflexible. So how do we build our own? A custom Pug is a map of metadata to metrics. So taking our SFlow example from before, we create a map or a hash or dictionary, choose your language, where the key is composed of all the attributes of the sample that must match, and whose value is the set of all metrics to be combined. In languages like Go, where structs are comparable, you can just use struct keys. You don't even really honestly need a different type. You can use the same type that you are currently using to carry the samples around with zeroed metric values. In other languages, you'll generate a hash of comparables. And then you just sort of maintain a tally, right? So the samples come in, do the key attributes in the sample match the entry in the map? If so, grab that entry's values, update the metrics. If not, you sort of add a new entry to the map with this sample's metric values. You flush that on a timer, which will sort of equate to your latency budget. And these can be placed, like I said, pretty much wherever you're currently buffering samples in custom code. They can also be implemented as wrappers around things like Kafka consumers and like I said, middleware and HTTP clients. They implement very easily once you've done it a few times. And like I said, you can absolutely enforce, right, the amount of latency that you're adding to the overall pipeline. So we can also do row reduction in the persistence layer. If you're using a storage layer like ClickHouse that supports aggregating tables, I personally love ClickHouse. I don't know if this is their first Monitorama. I was very happy to see them here and sponsoring. I feel like I should have seen them earlier, but I'm very happy they're here. The table that I reach for the most often when I'm working with persistence layer Pugs is the summing merge tree table, which honestly operates pretty much the exact same way as the custom Pug code that I just described to you. You give ClickHouse what they call a sorting key that consists of the columns whose values must match. And then you sort of specify aggregation functions on all of the columns that represent the metrics. So when ClickHouse encounters two rows that have been stored with the same sorting key values, it replaces them both with a new row that floors the timestamp and sort of contains the summarized metric values for both rows. This happens in the background, kind of over time. It's a beautiful thing, completely transparent to you and to distributed queries. You can also implement like an RRD tool style like rollups in this way. So you can manually floor the date timestamp over time, and Kafka will just sort of, and ClickHouse will just sort of naturally create these rollup tables for you. I don't know if anybody remembers what RRD tool was, but yeah. So yeah, it's super cool. It'll help you reduce your query time and storage costs, but it shouldn't be the only Pug in your system. Because again, for the umpteenth time, cost and latency generally increase as a function of traversal distance. So really you should have a bias for action, in my opinion, earlier in the pipeline stages. And none of this is to say that you shouldn't be using a grandiose streaming system, but absolutely you can be pugging before and after it, wherever it sort of makes sense for the workload is the point I'm trying to get across. I didn't mean to vendor bash. That's what I have for you. So enrich early, aggregate everywhere you can, sprinkle some Kafka on it. Don't be afraid to build pipelines that suit a specific purpose rather than just sort of farting everything into a lake just in case you might use it later. You can always like return to and build off the queue if you need to repurpose data for any new use cases. I love you guys. That's me.
We've got time for a couple of questions. I see orange shirt question here, and I do see you up there. I'll get you. I always miss you up top people.
How do you, this looks like it smooths out the data. How does it affect anomaly detection when you're basically having your fidelity? Yeah.
How does it affect anomaly detection when you're having your fidelity? Having?
I think he's mostly just kind of worried about data smoothing, right? Like that's the notion is that, it's an unforeseen agent in the data stream that's potentially altering the truth, which is a valid, right, like concern. Like sitting in the audience yesterday myself, it occurred to me at several points that, my pipeline design as stated in the slides may not directly apply to everyone's, especially like Netflix's, right, like workload. But I also do see, I think it's fair to say that even Netflix, in looking at traces and talking to their downstream users, have realized that many of their users, spans are cool, but many of their users, what they actually want is a summary of the span, an interpretation of the span. Let's not call it a summary. And so if you're using if you're doing sort of like anomaly detection, or you're doing span summarization, I also feel that like special purpose Pugs are probably going to get employed, or should be, right? Because Pugs don't necessarily, my use case is absolutely summing bytes for the most part, right? But we also do have these use cases where, like I said, we have distributed systems pinging each other inside of Fastly. So you have these use cases where like you're looking at basically what you can imagine to be ping data. which, you have the 10 packets, and then you have like that summary line beneath it, which is like, min, max, average, right? Like, so you sort of like pick the thing that's probably statistically relevant to your anomaly detection use case. And min, max, I feel like is, unless you're doing something really amazing, is still pretty relevant, right? So like if you have 100 samples, you know what I mean, and you're interested in anomaly detection, I feel like you could absolutely custom write a Pug that didn't just sum, that could absolutely perform some more. I feel like I just gave a second talk. Did I just give the second talk? Sorry.
Yeah. Tighten it up here. Anyway, I want to get you up there. Yeah.
Yeah. So if you have Pugs all over the stack, that's great for the reasons that you cite. But does it not also like kind of fracture the comprehensibility of the data that's coming through the pipeline? If you're changing it, aggregating at all these different points, do you need some sort of framework by which you can understand like how the data got to where it finally got, so that you can reason about it?
I am not nearly smart enough to summarize that question.
I feel like
If you could do that.
I feel like it was, maybe I'm misstating, but I feel like it was kind of a take on the first question, right? Which was sort of like, yeah, you're inserting an agent that's doing a thing that's going to hypothetically change the truth of the data set. And I feel like the idea that I'm trying to communicate is closer to a reduction in magnitude than a interpretation of the data itself. So, by all means, if you're looking at your data set and you're saying, look, this is trying to imagine a data set that, absolutely would require like a raw set of samples. At Fastly, it's a very large network. We can sample very drastically and still understand truth. And I know this because like we can compare a sample set of very fractional amounts of traffic, one out of every tens of thousands of packets, with literal interface counters. And match those signals together. Like I can say that this signal, which is so heavily sampled, this method of counting is so close to this literal value that like it doesn't really matter. And I think that I think the underlying power that I have there is the fact that I understand that body of data, right? So I would not suggest that you go and start just sort of like inserting summarization code into your pipeline where you don't necessarily understand what the outcome would be. I wouldn't suggest that to you. And I would also suggest that these do work very well when you have maybe a low label cardinality signal to compare the output to. Does that make sense? Yeah.
All right, if you would like a third conference talk, you're going to have to do it out in the hallway. Let's give a big round of applause for David.